change from a transformation form to just a basic rational form. Okay, so we're going to start off again. We're transforming rational functions, again a new function. So we're going to start with the base function y equals 1 over x. We're going to complete the table of values and sketch the graph. So by completing the table of values, substituting in each of my x values into my function, I get the following y values. I am now going to take each of these points, sketch them on my curve. So when x is -10, I get a value of -1/10. -5 is -1/5. -2 is -1/2. -1, this is -1/2. -1 is -1. At -1/2, my value is -2. At -1/5, my value is 5. At -1/10, it's -10, and so on. So as you can see, as my x values are getting closer and closer to 0, my y value should be getting closer and closer to the y-axis, but will never actually cross this y-axis. And when x is 0, if I substitute 0 into this expression, 1 divided by 0 becomes an undefined value. So what we get at our y-axis is a vertical asymptote occurring. And so in Math 20, we studied vertical asymptotes with reciprocal functions. This is just a continuation of those reciprocal functions. And so also, as we move forward, as x approaches -infinity, you'll also notice our y values are approaching 0. Okay? So what also ends up occurring is we get this horizontal asymptote at the x-axis of our graph. So here we have a horizontal asymptote. And the equation of that would be y equals 0. So on this side of the graph, all of our x values are negative, so are our y values. So what we get is we get a curve that's going to look something like this. So it's going to approach each of these asymptotes, but will never actually cross those asymptotes. Similarly, as our x values now become positive, same kind of thing happens. As our x values are approaching 0, our y values approach infinity. So this is like a really small value of x of 1/10 is 10, 1/5 is 5, 1/2 is 2. At 1 we get 1. At 2 we get 1/2. At 5 we get 1/5, and at 10 we get 1/10. So we kind of get this same type of graph here. As our x values get closer to 0, our y values are increasing to infinity. As our x values approach infinity, my y values are approaching 0. So we get this curve here, and this is called a rational function, where we get a curve that approaches always two asymptotes, a vertical and a horizontal asymptote. Okay, so we have to have a good idea of what this base function looks like in order to transform this function, just like anything else we've done with functions. Okay, so at a quick glance, our rational function at quick glance is going to look something like this. Okay, so let's talk about characteristics of this. Okay, so we introduced, and we've talked about them before in rational expressions from Math 20, are non-permissible values. So non-permissible values are what are the values of x that are non-permissible to the function. In this case would be x cannot equal 0. What happens as the graph nears 0, so as x gets closer and closer to 0, the y values approach positive or negative at infinity. Okay, so if your values, if we're coming from the left, if our values are negative, then it's going to approach negative infinity. If we're coming from the right side or positive, then they're going to approach positive infinity. The end behavior, so the end behavior means, well, what happens as x approaches infinite? So what does this mean? X is approaching positive or negative infinity. What's happening to the graph? So the end behavior on x, right, as x approaches positive infinity or negative infinity, the y values are approaching 0. Okay. The domain of this function, any rational function, will be all real numbers except for x cannot equal 0. So that's what our domain is going to look like. The range of our function is very similar. Is also going to be all real numbers except for y does not equal 0 as well. Okay. So we have an equation of a vertical asymptote at x equals 0, and we have an equation of a horizontal asymptote at y equals 0. Okay, so then if we can remember these characteristics of our rational function, then we can start to apply stretches to the function, right? So if we applied a vertical stretch by a factor of 5, what would the new graphing equation look like? So if our base function is this, 1 over x, and vertical stretch means I'm going to multiply this whole function by 5. Well, technically my new equation would be 5 over x, right? So if we were to think about what this graph would look like, so if we stretch this vertically by a factor of 5, the only thing that's going to change here is all of these points. So my asymptotes are not going to change, but what is going to change is this is going to be a little bit steeper of a graph. So for example, this point here at 1, 1 would become 1, 5, right? This point here at 2, 0.5 would be at 2 and 2.5, right? We're stretching everything by a factor of 5. So what's going to happen is this is going to be a little bit of a not as steep of a curve, but it's still going to take the same shape. Right? And same thing with your negative values, right? So anything that you're doing is you're just multiplying your positive values by 5, your y values by 5, and same thing in your negative values, right? So if we were to talk about some key points here, right? Normally on your original function at -1, this value would be -1. It is now would be -5. Same thing here. This would be a +1, +5. If this is still 0, this is still going to be an undefined value. Oops, sorry. And this would be undefined as well. Okay. All right, so I'm not going to go through the entire ordered pairs with you, but you kind of get the idea, right? For every y value, we're stretching that by a factor of 5. All right, so if we then applied a horizontal translation of 2 units to the right, what would the new graph and equation look like now? So if we went 2 units to the right, so we've already applied the stretch factor. Remember, a horizontal translation needs to be applied just to the x-coordinate. So I am going to subtract 2 as part of my denominator here. So 5 over an x minus 2 would show a horizontal translation. So if I translated this now 2 units to the right, well, everything is going to shift 2 units to the right. So that means that my vertical asymptote is going to move over 2 units to the right. And everything is just going to shift over 2 units. Okay? So this point of 1, 1 that became 1, 5, and same with -1. These points are now going to become, if I move 2 units to the right, are now going to become 3, 5. Oh, sorry, this should be -1. And +1, -5. Right? Because we're moving them, everything 2 units to the right. Okay? So I'm not going to draw my final sketch yet. I'm going to apply this one last transformation. If we then applied a vertical translation of 3 units down, what would the new graph and equation look like now? So now a vertical translation of 3 units down would mean I'd want to take this function and then subtract a 3 from the entire function. So now if I move everything down 3, again, this horizontal asymptote now is moved down to y equals 3. So then if we looked at these new points again, this 3, 5 would now be at 3, 2, and this 1, -5 would now be at 1, -8. So I've moved everything down. So then if I plot those points at, so 3, 2 is kind of a key point the graph is going to go through. The graph is still going to approach these asymptotes just like it did before. We're not reflecting at all, so it hasn't changed the area in which the graph occurs. And then the other point is at 1, -8, so the graph is also going to go through this key point. Okay, so what is our new graph going to look like? Something like this. And then the same thing here. Look like this. So after that stretch and then 2 transformations, this is what our graph is going to look like. So as a transformation, right, this is what our new equation would look like with our 2 asymptotes at x equals 2 now and our horizontal at y equals a -3. All right, so moving on. So the basic form for transformations looks like the following. Okay, so when we talk about transformations, we're going to see this a over x minus h plus k. Okay, and so the reason why there is no b value here is because technically our horizontal and vertical translation will always be combined into just one, a vertical translation, or not translation, vertical stretch. So the a value is basically a combination of a horizontal and vertical stretch. To be written as a vertical stretch only. Okay. Our h and k values are obviously our translation. So h is our horizontal translation. It also represents the equation of the asymptote. So this is the vertical asymptote value. And then our k value is our vertical translation, which is represented by the horizontal asymptote. Okay, and so our h value is obviously is what is going to affect the domain, and the vertical is going to affect the range of the function. Okay, so if we were to compare two different rational functions here, if we were to talk about the non-permissible values, the non-permissible values relate to our horizontal translations. So in this case, my non-permissible value would be x cannot equal 0. Here, my non-permissible value would be x cannot equal a negative 2. The domain of this function is affected by the h value so the denominator of my fraction, in this case, would just be 0. So your domain is directly related to your non-permissible value. So here would be x belongs to all real numbers, where x cannot equal 0. Here, x would be all real numbers, where x cannot equal a negative 2. Okay, so your domain is directly related to that non-permissible value. Okay, the range is related to the k value. So here my k value is 1. That means my range is going to be all real numbers, except for y cannot equal 1, because that's where my horizontal asymptote is going to occur. Here, my range value is going to be all real numbers, except for y cannot equal 0, because my k value here would be 0. Equations of the vertical asymptote. So the vertical asymptote relates to the x, or your domain, so it would be x equals 0, equation of the vertical asymptote. Here would be x equals negative 2. Horizontal asymptote here relates to my k value, which is y equals 1. And this would be y equals 0. Okay. So sketch the following function using transformations. So the first transformation I'm going to apply is a vertical stretch by a factor of 4. So really our transformations aren't any different than any other function. So if I were to consider this point, right, so it's always key to work off these 2 points. 1, 1 is going to be 1, 4, and negative 1, negative 1 is going to become a negative 1, negative 4. So I'm just going to kind of highlight those points. So these are my 2 new points after my transformation. Now I'm going to talk about my translations. So this is horizontal translation of 2 right and vertical translation of 3 up. This will also be represented by my horizontal and vertical asymptotes. So my vertical asymptote is going to occur at x equals 2. So at x equals 2, I'm going to draw a vertical asymptote, label it. I'm also going to draw a horizontal asymptote at y equals 3. Label that. Remember, it's just a sketch, so as long as you're fairly accurate and you've obviously labeled your asymptotes and then get a good idea of what your new graph is going to look like, you're good to go. So my graph is going to approach these asymptotes. I'm now going to move these points that I've created here that I've stretched. So I'm now going to move this 2 right, 1, 2, and 3 up. So my graph needs to go through that point there. And I'm going to do the same here. I'm going to move this 2 right and 3 up. And my graph needs to go through this point here. So what is my graph going to look like? It's going to approach these 2 asymptotes. So there's my stretch of 4. And there would be my new function. All right. So that is how we apply transformations. All right, the tricky part is quite often you're going to be given a rational function that is in this form. Okay, and what you're going to do in order to be able to talk about the transformations, you're going to have to change it into this form, the form that we just worked with. Okay, so basically what you're trying to create is you want to create an equation that is technically over one denominator into a fractional equation over two denominators, but this k value cannot have a denominator. Okay, so what we want to do is we kind of want to separate. We want to be able to cancel out this x's right now. Okay, so we want to separate this into two fractions. Okay, so what we want to do is we want to change this x into an expression of an x minus 2. So by doing that, I'm going to still multiply 4 by x, but instead of multiplying it by an x, I'm going to multiply it by an x minus 2. So the reason why we're doing this is so that these x minus 2's can eventually cancel each other out to create this k value. Okay? So what I'm doing is I'm basically subtracting a 2 from this x value and multiplying it